So our next speaker is John Clauser. He was born in Pasadena, California, US in 1942. He studied undergraduate physics at Caltech and Columbia University, New York, and received a PhD in physics from Columbia University in 1969. From 1969 to 1997, he worked at University of California, Berkeley, Lawrence Berkeley National Laboratory, and Lawrence Livermore National Laboratory. He is presently research physicist at his own private lab in Walnut Creek, California. So please join me in welcoming John Clauser to the stage to tell us about the development that led to this year's prize.
Oops, no. Wait a minute. I'm not connected. No. We're not, something is not right. Let me start over again then here. Okay. Okay, what I did in all of this was the first experiments to actually test what John Bell had shown us was probably one of the most important discoveries, I would think, of the recent decade, or the recent century, if in fact. So these are. So I will discuss the experiments, and then in order to understand the experiments, Mike Horn and I developed what's now called the theory of local realism, which is in essence Einstein's whole program for doing physics. And unfortunately, it's wrong, which is what the experiments show. And finally, I will end with the, does this work? Yeah. Discussion of why I still am totally confused about what's going on with quantum mechanics. Okay, let me start with the question is, what is quantum mechanics? What is quantum entanglement? Okay, quantum entanglement started out with Schrödinger. Schrödinger produced not one, but two important equations. He started out with the first equation, which was for single particles. In particular, hydrogen, which has a single electron. And miraculously, it described the structure and the energy levels of hydrogen. But more complicated was helium, which had two electrons. So he produces a second equation, which now involves two electrons. The two are very different equations. The second one allows quantum entanglement, which is a new solutions emerged from the second equation. And the peculiarity is that the two electrons are now intimately correlated. At the time, nobody suggested doing any experiments to test this rather bizarre prediction. However, both Einstein and Schrödinger were very disturbed by this phenomenon. And in fact, Einstein, Podolsky, Rosen in 1935 proposed the addition of additional variables to quantum mechanics in order to explain what's going on. Niels Bohr, on the other hand, said no, they're not needed. And I discussed all of this very nicely. So one of the first questions I was asked when I was talking about this in the Swedish embassy a couple of weeks ago was, what is a Bell inequality? This is what we, in fact, tested. There's not one, but there's actually three important Bell inequalities that I will talk about. The first, of course, was John Bell's 1964 inequality that Alain described very nicely. There's one problem with the theory. In order to be useful, a theory must make an experimental prediction. And unfortunately, John Bell's paper made no experimental predictions because it demanded a perfect experiment, and which had certainty in the outcomes. And as Ben Franklin pointed out, the only things certain in life or in nature are death and taxes. Unfortunately, this is not death and taxes. So with help from my associates, Mike Horn, Admiral Shimony, and Dick Holt, who is here in the audience, we produced the Clauser-Horne-Shimony-Holt, now commonly referred to as CHSH inequality, which was made the first real testable experimental prediction. So, and we proposed a detailed experiment to do that. And we noticed various important loopholes, one of which, of course, was mentioned that he tested, but a very important loophole was that the data really couldn't violate the inequality on their own, so we had to add some additional assumptions. So the third inequality is now was produced by Mike Horn and I in 1974, and it is the first loophole-free experimentally testable inequality. Okay, so start with the first one. Alain has already noticed. Einstein, Podolsky, Rosen had always, and others, had always assumed that quantum mechanics always made correct predictions. The grand irony of this Bell's paper is that he showed that Einstein's original intent of that paper was exactly the opposite of what was true. That if they wanted to show that the correct predictions led to the need for hidden variables. And what Bell showed was that if you put hidden variables in, then you can't get the predictions of quantum mechanics. So, again, I said it was not really testable. So, CHSH, in 1969, we were inspired by this work and wondered, well, can we really relieve get rid of Einstein's requirement for a perfect experiment? And indeed, we found that, yes, we could. And so we designed an experiment to actually test it. We worked out all the details of what you needed to do in order to test it. And that was the first actual hard experimental prediction. And it doesn't require Bell's impossible to achieve its conditions. So we now have two theories, two different sets of predictions, quantum mechanics and Bell's, or the CH inequalities prediction. So, being an experimentalist, let's actually do an experiment and find out which one is true. So, in order to do this, we had to add some minor supplementary conditions, but they were, we believe that they were quite reasonable and rather weak. Okay, the third inequality is the CH, or the Clauser-Horne inequality, that was developed in 1974, and it was to test what is now called local realism. We wondered when we were doing the experiments, we wondered, what is really being tested here? Is it just the addition of hidden variables, or is it something more profound than that? And we found that indeed it is far more profound. It was a test of Einstein's whole platform for doing physics, that we effectively were putting him out of business. And so and in fact, the theory, when we developed it, was effectively dead on arrival. It was already refuted. But nonetheless, we tried to put it in as clear as possible set of terms as we could. So, and in the process, we formulated a new inequality, the CH inequality, and it allows loophole-free tests. So now, if with some even milder additional assumptions, then the first experiments that I had done, 72 and 76, actually knocked it out, so that it was already dead. More recently, and it's taken a long time because the technology did not exist at all in order to test it in 1974, it has now been tested conclusively. So now, without any loopholes at all, one can say, and I agree with Alain's early conclusion, it's dead, Jim. So, what are some of the experiments? There are three important ones that I did. First was with Stu Friedman, who was a graduate student at UC Berkeley. We published the results in 1972, and this was the first experiment to actually test the CHSH inequality. In parallel with us, Nicole, I mentioned, who is here, was working with Frank Pipkin at Harvard. And they got the opposite result. Whoops, one of us is in trouble. So they decided not to publish. They were skeptical of their results. But now I'm skeptical of my results. So what do I do? Well, I decided, I needed to repeat their version of the experiment, which I did in 1976. And then just along the way, one of our assumptions had, and I was kind of searching for loopholes, had required photons to act like particles. But I discovered that there was no actual experimental proof that photons did act like particles. So I did an experiment in 74 to prove that. Okay, so here is the first experiment, a picture of it, and that at the right end, there's a very young Stu Friedman. In the middle is an atomic beam apparatus sitting there pumping away, oil leaking all over the floor, pair of polarizers on each side, which would rotate. So, and this became Stu Friedman's PhD thesis at Cal Berkeley. So what we did is we had a calcium atomic beam, and we excited it with this UV lamp. Very weak extension. We wished we'd had lasers, which didn't exist at the time. So we got 6.3 sigma result. I mean, the 5 sigma criterion that is now common was invented by Louis Alvarez at Berkeley, and he was a strong taskmaster on any experimental results that came out of Berkeley. So this was the second experiment which I did. I mentioned this was a repeat of the Holt-Pipkin experiment. I used the same polarizers, but I used their source of mercury for emitting, creating the two photons. And Dick Holt very generously taught me how to do it. It's not an easy, and that is my Nobel artifact that I have donated, is one of the sources. So it used mercury with an electron beam exciting the atoms, and I got at least a 4 sigma result there. And we used the same protocol in order to introduce the assumptions. So the other experiment that I mentioned had to do with, was there a real wave, experimentally demonstrated wave-particle duality for photons? Photons started in 1917 when Einstein was trying to explain how does a gas and a thermal, a Planck spectrum of light come to thermal equilibrium with each other. And he noticed that photons had to behave by what he called directional energy bundles. We now call them photons. Then Schrödinger noticed that, what's the difference between, asked the question, well, what's the difference between a particle and a wave? Well, a wave could be just a classical pulse of light. And that is commonly referred to as the old Schrödinger interpretation. So how does one tell them apart? Suppose you have a source and you send light through a half-silvered mirror. If it's a wave, the wave will go both ways, reduced intensity. If it's a particle, the particle will go one way or the other. Now, if I have two detectors behind the half-silvered mirror, if it's a wave, they will both see this pulse, and there will be a finite probability that both will register simultaneously. If it's a particle, only one of them. So how does one do that? So actually, Schrödinger suggested this, and Janissy in Budapest actually tried it, but unfortunately they did an inconclusive experiment. So I went back and figured out how did one do it totally conclusively, and so I did it actually where using the same source that I used for the producing for the mercury Bell's theorem experiment. We had photons going in both ways and two half-silver mirrors, and using some work by Glauber's formulation, one could show that the coincidence rate between here and here, there should be none, of course, if it's a particle, but there should be an anomalous, if it's a wave, coincidence rate. The product of these two coincidence rates here and here must be greater than the product of these coincidence rates. And so here are the data, and it's quite the opposite by about 20 sigma. So indeed, particles do act, photons do act like particles. So, as I mentioned before, Mike Horn and I were trying to understand what it is that Bell's theorem experiments actually say. So we developed what's called the theory of local realism. Originally, we called it objective local theories in our first paper on it. And it's an extremely general theory that takes into account all of the basic elements of Einstein's platform. And along the way, we produced the CH inequality, which is actually a hard experimental prediction with no loopholes. We did not have any assumption of causality, which we had earlier on. There was no behavior requirement for a particle-like behavior. And then there was some discussion among various other workers. John Bell and Admiral Shimony added additional components. So presumably it is better called Bell, Clauser-Horne-Shimony local realism. It's very short-lived, as I mentioned. It was already dead on arrival. But that wasn't good enough. It had to really be shown to be dead with no loopholes by testing. Okay, what does it assume? Local realism is extremely simple theory. Anton Zeilinger, and please quote me, tell me if I'm misquoting you. At one point, he at a conference, he said, if Bell's inequality and local realism had been discovered before quantum mechanics, it is so reasonable it would have been taken as a law of nature, or adapted as a law of nature. Unfortunately, it's wrong. So, what does local realism assume? It assumes that nature is made out of stuff. What is stuff? Well, we may not even know what it is. It is, it is what Einstein, Podolsky, Rosen referred to as elements of reality. It's what we call matter, or what Clauser-Horne called objects. John Bell referred to it as Beebles. It's there, it's distributed throughout space. Now, actually, Einstein's whole program, and general relativity in particular, goes a lot further. And he says that, well, it has a finite mass energy density, and it is that density that determines the whole geometry of the universe. We don't need that for local realism. All we need is that it's there. So it could evolve stochastically, or it can evolve deterministically. We don't care. It's stuff you can put in a box. You could surround it, and the stuff that's in the box, if you're doing an experiment, the stuff determines the probabilities of the experiment that you actually do there. We assume that there are real results that happen when you do an experiment. That is, unlike Schrodinger, actually, he thought the whole idea of the cat in the box experiment was a total absurdity. We assume that the cat is either alive or dead, and we just don't know which. That a real result always occurs. We assume that the properties of the stuff determine the results of an experiment you do. If you have a parameter setting on your apparatus, and then you change the parameter setting, presumably you will get a different result. So, what does it predict? Well, suppose you have two very widely separated boxes. Each has stuff in it. and you're doing experiments in these two widely separated boxes. The assumption following Einstein's requirement for locality is that stuff in one box and the parameter settings, the result of the experiment in one box measuring that stuff cannot be influenced by the parameter setting choice made in the distant box. That's all you need to produce the Clauser-Horne inequality. Okay, so here's what are boxes? Well, they're just closed surfaces. They separate, each closed surface has an inside and an outside. So here we have a pair of boxes. Okay, these characters are, well, I made that drawing in 1976 before the characters had been named Alice and Bob. Well, okay, so this, but she's perhaps trans, I don't know. So, here we have Alice and Bob making measurements, and they get a result, yes, no, on each side. So we have our boxes here are now shrinking at the speed of light. And so they're drawn so that we're doing the experiments when they're space-like separated. So if I plot in versus x in time, here are the boxes shrinking simultaneously and doing experiments. So the assumption is that stuff back here in the common overlap region is what is the result of the experiments. If you read some of John Bell's stuff, you have to be careful. For some reason, he had these reversed. He had the arrow of time going to the left. I'm sure he had a reason for it, but I don't know what it was. Okay. It's dead, Jim. Apologies to Star Trek. It was, for a long time, it was very difficult to do. The technology just simply did not exist back in '74, but it has improved. So it became very important to eliminate the loopholes in the earlier tests of the CHSH inequality, and to really do a loophole-free experiment. And finally, most recently, at the labs in Vienna and in Champaign-Urbana, Illinois, it has been totally killed dead. Okay, now I will use my time remaining to make a value statement, if you will, about why I have the faintest idea what's going on. And I argue that, in fact, there's been an elephant in the room, pardon the metaphor, that has been hanging around ever since Schrödinger and EPR. Remember that Schrödinger produced two very different equations. He had one for hydrogen with only a single particle, and he had another one for helium, which had two particles. Nobody seemed concerned at the time about the fact that these two equations were formulated in very different spaces. And they are what I believe is improperly linked, and I'll go on to that in a minute, by what I call Born's ambiguity. Born was the one who said that they are equivalent. And this has been, the elephant's been hiding in plain sight. And I noticed that, in fact, the Einstein-Podolsky-Rosen debate, Bohr debate, was never really settled. Various textbook authors believed one or the other of the authors, and they're developed in the literature, in the textbook industry, two very different schools of thought. And most people never seem to notice this. But with the advent of local realism and quantum entanglement, then it became clear that one could actually contrast and identify these two schools of thought. Okay, school number one, I assert, is essentially a form of local realism. So, what are the textbooks that promote the school number one? It is what I call the laboratory space formulation of quantum mechanics. Okay, it was taught, these are all, I kind of cut off the list at about 1980. First was Born's textbook. Two very important textbooks, familiar, Dickey and Whitkey and Merzbacher were very popular. All follow this. And like, for example, in Born's case, the waves are propagating in the lab. And he shows pictures of waves moving around. All of these books show waves propagating through a two-slit experiment in lab space. Feynman, this was his review article, 1948, even puts it into the title. This is a space-time relation. French and Taylor used at MIT, and of course, the original classic Schiff. Okay, what is school number one? Quantum mechanics for single particle systems is formulated in lab space, or real space, the XYZ of this room. There is a point, every point in this lab space has a vector to it, and Schrödinger's wave function is a function of its position in the room, or in the lab. And more importantly, the probability density, psi star psi, is a function of its position in the room. It is the evolution of these waves is governed by Schrödinger's equation in lab space, and it depicts waves of probability. You probably heard any number of people describe quantum mechanics as waves of probability. Moreover, there's also defined by Born a conserved probability current, which flows like a fluid through the lab. And he famously used that current to describe flux conservation in Rutherford scattering. Unfortunately, it only works, the school of thought number one only works for single particle systems. It cannot describe two particle systems, and it cannot describe entanglement. So what's school number two? Also had a large group of textbooks which very specifically said, we are in configuration space. Okay, probably one of the most important ones, but Bethe and Salpeter, with the authoritative work on hydrogen and helium, Bjorken and Drell, relativistic quantum mechanics, Kahnen and Shortley, how you calculate spectra of atoms. Landau and Lifshitz, great quantum mechanics textbook, was translated by John Bell, actually, and Messiah's famous book, except he claims he's in configuration space, but actually he cheats a bit. And probably most importantly of all was von Neumann's textbook. Okay, what is the configuration space school of quantum mechanics? It is very, very different from what I just described. The wave function depends on a system's degrees of freedom. There could be many of them. There could be k degrees of some large number k, and so we have a wave function, and these are all, this is straight out of von Neumann's book. So if you have, say, two particles in helium, then now the argument space of the wave function is very different. It has an xyz of particle 1, xyz of particle 2. Wait, our lab does not have 6 dimensions. Something has dramatically changed. Importantly, the position in the lab is not one of the arguments. That means that its value is the same everywhere in space, unlike the lab space formulation, where it's different every point in space. So Schrödinger's equation now is very different. It's describing the evolution of particles in this configuration space. It's an abstract mathematical space. It is not at all the space that Star Trek was exploring. A few important, and it's absolutely required if you want to discuss more than one particle systems. Born's conserved currents cannot be drawn in configuration space. Green's theorem does not apply. More importantly, there is no prohibition for propagation of signals faster than light in configuration space. It's a purely arbitrary space. Totally abstract. It's what the mathematicians call a vector space. Not at all. So, it has been asserted, and as far as I could trace back, this was originally to Born's talk, that these two cases are the same. They are not. Clearly, the two wave functions are very different. They are not equivalent. One depends on the position of space, one does not. There are no associated probability waves for configuration space. So, for my last slide, I will describe why I find this all totally confusing. You gotta have configuration space in order to describe more than one particle systems. But there's no reason that the special case of single particle systems should be any different. So you need, and we notice really that the lab space formulation is really a form of local realism. It's dead, Jim. So, now all of these great models, conceptual models of probability waves propagating in space are also dead. The flow of currents, probability currents, are dead. I don't know how to visualize propagation in configuration space. There are a lot of people here who know a lot more quantum mechanics than I do, and maybe one of them will help me understand what does it mean to have a wave propagating in configuration space. I don't know. Dickey and Whitkey and Merzbacher were on my side. They both gave up and said, oh, gee, this is all our great models, i.e. our earlier sections of the book we really should throw away. So I have one final challenge to my theorist friends, if I still have any. Remember we said that general relativity is a form of local realism. So, and it is a general relativity that, for example, gives us black holes. So, but that's all formulated under local realism theory. So my challenge is to the theorists, is it possible to have two entangled black hole spins? Thank you.